Consider the classical game of rock, paper, scissors, where paper defeats rock, rock defeats scissors, and scissor defeats paper. Alice and Bob are playing a game of rock, paper, scissors, and the moves that Alice will perform in each of the n rounds are predetermined. Suppose this is the set of moves that Alice will play in round 1 to n. You are playing as Bob and your goal is to win the game. You will win the game if the total score obtained by you in all of those n rounds is strictly greater than the score obtained by Alice. For example, in this configuration, all the rounds that are marked as green were won by Bob, and all the rounds which are marked as red were won by Alice, and all the unmarked rounds were led to a draw. Now you can see that since Bob won 4 rounds and Alice won only 2 rounds, therefore 4 is greater than 2, and this is a valid configuration. So the scoring rules are every time a player wins, they get +1 point, and if a round leads to a draw, then nobody gets any point. Your goal is to find out the total number of configuration where the eventual winner of the game would be Bob, and the total number of rounds that is possible can be as high as 10 to the power 3. Take a minute to pause this video and think of a solution before you watch this video. This problem is essentially a rewording of LeetCode 3320, count the number of winning subsequences, which appeared as a third problem in a recent LeetCode contest. Before we solve this problem, let us simplify things a bit. Instead of tracking two scores, that is the score of Bob and the score of Alice, can we track a single score so that we do not have multiple entities to deal with? If you rearrange this equation, you will notice that Bob will win if the difference between these scores is strictly greater than 0. So instead of relying on the original scoring system which awards points to the winner, let us define a new scoring system where only Bob will be awarded points. That is, if Bob wins, he will get +1 point, but if he loses, we will also deduct 1 from their total score that have been accumulated so far. In this new scoring system, you will realize that if the total score of Bob is strictly greater than 0 after all the n rounds, it means that Bob has won strictly more rounds than Alice, and therefore that configuration is valid. With this modification, we now only have to track a single entity, and this simplifies things a bit. Now let us move on to the actual solution. If there are n rounds and Bob can perform any of the moves, that is rock, paper and scissors, in each of the round, the total number of configuration is equal to 3 to the power n, which can be as high as 3 to the power 1000, which is a pretty huge number. But let us look for optimizations later in the video. Right now our goal is to construct all these 3 to the power n configurations. But notice that not all the configurations would be legal, because some of this configuration would lead to Bob losing the game. But let's not worry about that right now. First we will try to construct all the configuration, and at the end we will discard the configuration which are not legal. So suppose we are playing a game of 4 rounds, R, S, R and P. So this is the move strategy for Alice. Now of course there will be 81 different configurations for Bob to play. And suppose you have enumerated all these 81 configurations either by hand or by brute force or by some algorithm. So you collect all these 81 configurations and store it inside this green box. That is, every ellipse that you see inside this green box represent a possible configuration to play the game on 4 rounds, and we know that there will be a total of 81 ellipses inside this green box, and this is one example configuration that is possible on 4 rounds. Now what would happen if you append a new element at the end of Alice's strategy. That is, now you want to play a game of 5 rounds instead of the originally planned 4. With these 5 rounds, we of course know that the total number of configurations will now be equal to 243. But can you devise a strategy to construct these 243 ellipses for this green, for this yellow box, using only the ellipses from this green box? Because we had assumed that you had manually enumerated all of these ellipses, but now we need an algorithm to transfer from this box to this box, because if we can do that, then that would be the essence of the dynamic programming solution. And if you know how to transition from here to here for the naive set construction, then you can also solve the optimal version of the problem. So let us try to see how we can do that. Let's pick any element or any ellipse from this green box. Suppose it is SPRS. It means that Bob has already performed his move on these 4 rounds, and we can simply take these moves as is for the first 4 rounds, and for the last round where Alice plays rock, Bob can either play scissors, rock and paper. So let us append these letters to this configuration and we will achieve a configuration of 5 rounds. But notice that all of these 3 configurations would be unique. Why? Because there are 81 unique ellipses here. So if you pick a unique ellipse and append a unique element at the end, all these 3 entities would be unique. And in fact, you will realize that every ellipse that is present over here must have been constructed from an ellipse over here, because if you consider this example, this means that you took out an ellipse representing SPRS from this box and you appended either scissors or paper or rock and achieved this configuration. So now we have a strategy using which, given this box, you can construct a new box if you append an element at the end. That is, if you were to increase the number of rounds. But the time complexity is still 3 to the power n, because we are enumerating all the possible configurations and then we were later planning to discard the illegal ones. But how do we optimize the time complexity? To do the optimization, notice that even though there are 81 ellipses inside this green rectangle, some of these ellipses are pretty similar, even though it might not look like it. For example, consider these 2 ellipses inside that first rectangle of 4 rounds. This is SRRP and this is PPRP. Even though they might look very different in what is being written, you will realize that the only thing that matters for the end is the score of Bob in these 4 rounds, and the score of this configuration is +1 and the score of this configuration is also +1. There might be a typo in the image and the score of this might be 0, but for now assume that it is +1. So since the score of both of them is +1, they are essentially identical, because we don't really care about what moves Bob performed in a particular round. We only care about how much total score has he accumulated so far, because we know that all the rounds are independent. So that is why only the score of the previous rounds matter, not the actual contents. So now that we know that some of the ellipses here would be identical, let's club those identical ellipses and we will say that they are identical when their scores are identical, and store them inside a rectangle. So this rectangle will have all the ellipses that have a score of 5. This triangle would contain all the ellipses that have a score of 2, and this triangle will contain all the ellipses which have a score of -9. Now notice that in this triangle, all the ellipses are essentially the same. So we don't really need to create all these 7 ellipses. We don't really need to track them anymore. We only care about how many ellipses are there, because that means that we only want the total number of configurations that will lead to this particular score. So we have essentially found out a way to partition the set of 81 elements over here into equivalence classes. And how many equivalence classes are there? So the equivalence classes can be uniquely represented by an integer from -n to n. So there are 2 into n plus 1 equivalence classes. So therefore there will be 2 into n plus 1 rectangles sorry, there will be 2 into n plus 1 triangles that you see over here. So now from this 81 we are now down to just n, or 2 into n plus 1. So we have reduced the number of elements that we need to track by a huge amount, because previously it was exponential, now it is just linear. And we only need to track the number of ellipses, which is essentially the size of this triangle, which is 7. And you will notice that each ellipse will essentially land inside one of these triangle uniquely. Therefore the total sum of all of these triangles would be equal to the total number of ellipses that we began with, which is equal to 3 to the power 4. So now all we have to do is figure out how to transition from this rectangle to a new rectangle that defines a configuration of 5 elements instead of 4 elements. So let's do that. Let's start with a triangle where all the ellipses inside of it have a score of +9. So now we are not really tracking the ellipse anymore, we just know how many ellipses are here and their score is +9. Now in the last round, Bob can either play scissors, rock or paper. And since Alice played rock, his score can either be -1, 0 or +1 depending upon what he plays. Notice that all the ellipses in this triangle will now behave identically, that is they are homogeneous, because if Bob has played scissor in any of these ellipses, the score of all of these ellipses would reduce by 1 and it would become 8. Similarly, if Bob plays rock, then the score of all of these ellipses would remain same, and if Bob plays scissors, then score of all of these ellipses would increase by 1. Therefore you now have a strategy, that is start with your old set which contains some triangle, and this triangle have some ellipses inside of it. We don't really track the ellipse anymore, we only track the number of ellipses inside here, and this triangle will be uniquely represented by the scores that they have. Then with each triangle try to append either S, R or P to each of the elements here, and then it will lead to a triangle in this section for R is equal to 5 rounds, and you transfer this triangle from here to here. So the equivalence class of this triangle changes. So the equivalence class of this triangle was +9, but after appending S it has become +8. So we have now found out a way to transition from one equivalence class to another after you append a new elements. And with this you know that there can be order of n triangles. So every time you append an element you only need to do O of n operation. Therefore the time complexity of the overall algorithm would be O of n square. So now this is the formal definition. So the DP definition is DP of S represents the number of configuration which achieves score is equal to S, and you will realize this S is nothing but the equivalence classes, and the DP value is nothing but the number of ellipses that land inside that triangle. And how do you perform the transition? You will notice that if you have this old set and you have this bigger set, the new set with more rounds, then in the new set, if you consider any rectangle with equivalence class of S, it must have been constructed by taking an older rectangle of equivalence class S-1 and playing a move that led to a score increase of 1, right? So that is why the score became S. Or taking a rectangle or taking a triangle with equivalence class +1, S+1, and then playing a move with -1. Similarly, taking a triangle with equivalence class S and playing a move that resulted in no change of score. Therefore, if this is the NDP array and this NDP is nothing but the new rectangle that we are creating for these 5 rounds. So if this is the NDP array, the NDP can be constructed by using the triangles from these 3 equivalence classes of the previous DP array. And using this technique we have optimized the time complexity from 3 to the power n to O of n square into log n. Now why do we need this log n factor? Realize that the score can also be negative because it can range from -n to n, and you cannot store negative indices in an array. Therefore we will use a map and this map introduces a log n factor. So you see that we were able to solve this complicated problem from exponential, which was 3 to the power 1000, to just O of n square, which is a huge improvement. So we did it using dynamic programming, and this idea of equivalence classes that I have discussed is pretty common in dynamic programming problems, and I even have a video on my channel which is a bit advanced, where I talk about this idea in more detail, but that is geared more towards code forces. Now, the original LeetCode problem that I talked about wasn't so simple. So it had a slight variation, and the variation was that you need to find out the number of valid configuration where Bob wins. However, Bob cannot play the same move twice in a row. That is, Bob cannot play rock followed by rock, paper followed by paper, and scissors followed by scissor. How do we solve this version? That is, how do we find the number of valid configurations for Bob in this restricted version of the game? If you try to apply that same strategy of taking the old triangle and constructing a new triangle, you will see that it is no longer valid. Why? Because the elements are not homogeneous anymore. Because even if all the ellipses have a score of 9, when you try to perform a move of rock at the last round, then some of these ellipses might allow that move, because in these ellipses the last round was not rock, and some of these ellipses might not allow that move. So these elements are not homogeneous anymore, right? And we have discussed that to partition a set into equivalence classes, all the elements in one single equivalence class should behave identically or homogeneously. So how do we create a new partition? To create a new partition, notice that we of course need the older partition, which is partitioned on the score of that ellipse, plus we would now also need to remember the last round that has been performed on each of these ellipses, and all the ellipses that have identical score as well as identical last move. So this thing might contain multiple ellipses where the score is 9 and the last move is also R. Then for these ellipses we don't really need to track them anymore. We can just club them together and store it in a rectangle instead of a triangle. So in this rectangle we just need to remember how many ellipses are inside of it. So we have now found out a way to partition this set into equivalence classes, and each equivalence class will be uniquely represented by the score of the configuration as well as the last element of the configuration. And now you can see that all the elements in one equivalence class will be behaving homogeneously. Why? Because if you pick this ellipse, for this ellipse Bob cannot perform rock as the next move, but that is true for this ellipse as well, that is true for this ellipse as well. So now that the elements are homogeneous, we have a valid partition. Now let's talk about how to perform the transitions. That is, if this is the older equivalence classes of 4 rounds, how do you append a new round and create the equivalence classes for the 5th round? So to do that, let's start with one equivalence class which is represented by +9 and last move was rock. In this equivalence class there can be multiple ellipses over here. Then in the next round Bob can either play scissors, rock or paper, but this move will be blocked not just for one ellipse but for the entire set of ellipses inside this equivalence classes. Therefore we can simply block this move for this entire equivalence class, but for this and this move all the ellipses behave identically. So all the ellipses in this equivalence class will now move on to the equivalence class of 8, because all their scores would decrease by 1, but we were also tracking the last move for that ellipse, and all the ellipses will have scissors as their last move. So they will jump from this equivalence class of +9R to the equivalence class of +8S, and we can do the same thing for here. So now we have found out a way to partition this into equivalence class based on 2 dimensions, but after the partitioning all the elements are now behaving homogeneously, and then we can try to see how one equivalence class jumps from here to here. So this is the formal DP definition, where DP of D comma last represents the number of configuration where the score is D and the last move is last. So this dimensions are nothing but the partitions that are needed for the equivalence class, and this DP value is nothing but the number of ellipses that reside inside the triangle, inside the rectangle that we have defined over here. And to perform the transitions, we have already discussed that all you have to do is iterate over each of the equivalence class, that means iterate over each of the rectangle, and then perform your move by choosing either rock, paper or scissor, but make sure to block that move for that equivalence class if the next move is same as the last one. And this equivalence class of D will jump to the equivalence class of D plus score depending upon what the score is after performing that move. So now we have figured out a way to do the transitions in O of n. Therefore, the total time complexity of this variation is O of n square. So let us talk about the code. We'll divide the code into multiple sections. In the first section, we want to simply write out a function that returns the score of Bob, because we have defined our new scoring system. So it just takes the move by Alice and by Bob, and then it returns either 0, +1 or -1 depending upon whether Bob won or lost. Now you will notice here that I am not exactly using rock, paper and scissors, and instead I am using something like as F, E and W. This is because the original problem on LeetCode had different naming convention for rock, paper and scissors, but that is not something that you need to worry about right now. And then this is the actual code fragment. So here you see that I have defined the DP array, and since we need negative scores, we will use a map, right? Because an array cannot handle negative indices. And so these are the partition for the equivalence class, so the score and the last move, and this value is nothing but the number of ellipses inside that rectangle. This is the base condition, and this base condition is nothing but the thing that we discussed at the start, where in order to do these transitions you first need to come up with a manual enumeration of some of these smaller rounds, so that this algorithm can now iterate over all of these elements and then produce this new set of elements for the bigger round. So this is the base case that I have enumerated by hand. Now you try to append one round at a time, right? So you try to append one round at a time, and then you have to refresh the DP value. And by refresh the DP value, I mean that you start with this set of configuration and then you move to this set of configurations by transferring the equivalence class of this to this. And how do you do that? You iterate through all the equivalence class, and equivalence class is uniquely defined by the score as well as the last move, and the score can vary from -n to n. So these uniquely define the equivalence class. After you have determined the equivalence class, you freely make your move. It can either be rock, paper or scissor. But if it is same as the last element of the representative of the equivalence class, then you are not allowed to perform that move. Otherwise, simply perform that move, get whatever score that Bob gets, and then transfer this rectangle to a new equivalence class in this new container. So that is why this equivalence class gets transferred to here, and then you simply swap this DP with this new DP value, because at the end of the loop you want the answer to represent 5 rounds, right, instead of the previous 4 rounds that we discussed. And this is just it. This is the simple code that solves the problem on LeetCode. To find out the answer, you can simply see that all the equivalence classes that represent a positive score, regardless of their last move, is a valid choice. So you count the number of ellipses in all of those equivalence class and you get that answer. Now the time complexity of this algorithm is O of n square into log n. Why log n? Because you are using a map over here to handle the negative indices. Now this complexity is good enough, right? Because the DP section of this video ends right here. Because if you really understand how this map DP is working, then you have really understood how DP is being applied to this problem. However, in the LeetCode contest, the constraints were a bit tight and n square log n was not allowed to pass, at least for me in C++. So they actually needed an O of n square algorithm. But this O of n square optimization from O of n square into log n has nothing to do with dynamic programming anymore. So at this point, if you were watching the video just to learn the concept of dynamic programming, you can stop this video. But if you are interested in learning about the optimization from n square log n to O of n square, you can keep watching. So how do we remove that log factor? To do that, we need a mechanism to handle negative indices for an array, right? To handle negative indices, realize that the score can only vary from -n to n. So instead of accessing array of -3, why don't we add an offset to each of these scores? That is, every time we want to access a of I, let us access a of I plus offset, and let us define offset big enough such that it reduces all the negative indices and brings it down to 0. That is, if you choose the offset as n, then if you add plus n to every score, then the minimum score would be -n plus n, which will be equal to 0. And now the score are in range 0 to 2n, and your normal array would apply. So all you have to do is maintain an offset, and every time you want to access a of I, just access a of I plus offset instead. And every time you want to update a of I, just update a of I plus offset. So this idea looks pretty simple, but I still wanted to add this section in the video so that you can see an implementation that you can reference for the rest of your LeetCode journey, because in a lot of problems you might need to deal with negative indices. So this is the final version of the code that runs in O of n square, and in this code all I have done is taken this O of n square log n code, and then I have simply replaced all the map access with array access. But every time I am accessing the map, I added an offset over here. So offset over here, and every time you access a map, you add an offset so that you can handle the negative indices. So because now the indices are in 0 to 2n, and you will also remember that we had this character as the second entry, but to handle that character, all you can do is create a vector which represents rock, paper and scissor, and instead of tracking that character in your map, just track the index of the character, which is an integer, which can be easily done in an array. Therefore this problem can be solved in O of n square. The rest of this code is exactly same as O of n square log n. Similarly, if you want to get the answer, you simply, previously you were querying dp of d comma last, now you query d plus offset. So this solves this problem in O of n square, and I believe this was a pretty educational problem for beginners to dynamic programming. And the reason why I say that is because I looked at the contest submissions, and a lot of people were not able to solve this third problem during the contest. But when I read the problem, I was able to come up with the solution within a minute. And that really indicates that a lot of people are not familiar with how to apply dynamic programming to new problems, because I think this is a fairly standard application of the equivalence class idea for this problem. So if you want to dive deep into this, you can also take a look at this video on my channel called Dynamic Programming Mindset, where I talk again about these equivalence classes in DP problems, but keep in mind that this video is a bit advanced and geared more towards code forces. However, even if you don't watch this video, the concepts that I have discussed in this video will help you in your dynamic programming journey later in LeetCode. And in fact, I challenge you that for any LeetCode problem that you might come across in future where you are using iterative DP, if you think long and hard enough, you will realize that it has some representation of these ellipses, triangles, and these boxes of equivalence classes, right? And you can actually use this as a template problem to try to solve any new dynamic programming problem that you might come across. And all the codes that I have discussed in this video, as well as the slides for this video, I will link them in the YouTube description, so that if you want to revise this concept later on in your LeetCode journey, you can simply go through the slides instead of watching this video again. I know that this video was a bit long and I might be speaking too fast at certain places. My voice might not be legible at some places, but even after all of these flaws, if you still like the format of this video, do let me know in the comment section down below, so that I can add more content of this format on my channel for LeetCode. And if you have any more suggestions or improvement, do let me know in the comment section down below.